Now I am discussing about the applications of first law of thermodynamics, which is a very important topic in all the entrance examinations, whether it is NEET or IIT JEE for chemistry students. So in this, right, we know that first law equation is given by du is equal to dq plus dw, where the right hand side represents the small amount of heat interaction between the system and surroundings and the small amount of work done between the system and surroundings. So the right hand side totally is nothing but the energy interaction between the system and surroundings. As a result, what happens? The internal energy of the system will change, du will change. The internal energy of the system will change, du will change, right? Okay, so this is the equation of first law. Now, I am applying the first law of thermodynamics to different thermodynamic process. The first among them is isochoric process. What is the isochoric process? Isochoric process is a constant volume process. In this, the volume of the system is constant, okay? Volume of the system is constant. Therefore, no increase in the volume, no expansion, no decrease in the volume, no compression. So, change in volume is dV is equal to 0. Now, in any reversible process, the expansion work or the compression work or the mechanical work is given by dW is equal to minus PdV. Minus PdV. This formula is applicable for any reversible process where there is a small change in the volume of the system, dV, okay. So, the work done dW is given by minus P into dV, but in this process as volume is constant, therefore, the work done is always 0. This is a key aspect of isochoric process. In isochoric process, as volume is constant, no expansion is possible, no compression is possible, and no change in the volume is possible, dV is equal to 0. As a result, the expansion work or the compression work or mechanical work or PV work becomes 0, okay, right. So, the work done, right, that is due to expansion, the work done due to compression, right, okay, that is mechanical work is always equal to 0, right. This is the key point. Now, from first law, right, what is the equation? We have du is equal to dq plus dw. As work done is always 0 in this process, substituting here, what we will get as dw is 0, du is equal to dq at constant volume. Okay, this is the application of first law for isochoric process, right. If the changes are measurable, significant, then the same equation 3 can be written as delta U is equal to Q at constant volume. What is Q at constant volume? Total amount of heat interaction between the system and surroundings at constant volume, okay. So, delta U is equal to QV. What is the meaning of this equation or this equation 3, okay? The amount of heat added to the system at constant volume in this process always results in internal energy changes of the system, because here no work is done. So, whatever amount of heat is added, it is just increasing the internal energy of the system, okay? It is just, right, changing the internal energy of the system, okay? Suppose if heat is given out by the system, then what happens, right? The internal energy of the system decreases, okay, right? So, therefore, here whatever heat is added to the system or removed from the system is just changing the internal energy of the system, okay, because in this process no work is done. So, whenever the word isochoric process is used, immediately as volume is constant, the work done is always, the mechanical work, the expansion work, the compression work is always equal to 0, okay, right. As a result, the first law application for isochoric process is Q at constant volume is equal to delta U. Here no work is done, okay, right. Now, I am, right, just reminding you the definition of heat capacity, right. What is the definition of heat capacity? Heat capacity of any substance is defined as the amount of heat added to a certain amount of mass to rise its temperature by 1 degree is defined as heat capacity, okay, right. The amount of heat added to a certain amount of mass to rise its temperature by 1 degree is defined as the heat capacity. The units are Joule per Kelvin, okay. Now, I am defining the heat capacity of a gas at constant volume, because for gases we calculate the heat capacities separately at constant volume and separately at constant pressure, because there is a lot of difference between these two values, okay, right. So in case of gases we do it, in case of solids and liquids, right, we usually measure the heat capacity at constant pressure, and the difference between the heat capacity at constant pressure and constant volume is very less in case of the incompressible substances like solids and liquids, whereas in case of compressible substances like gases, the CV value and CP value differ by a significant amount, okay. Therefore, we are calculating heat capacity of a gas at constant volume as the amount of heat supplied to a gas, to a certain mass of gas, to rise its temperature by 1 degree at constant volume is defined as CV, okay. Now, this is equation 6. Now, right, okay, for any gas, right, okay, internal energy depends both on temperature and volume. Means if volume change is there, then the internal energy may change. If temperature change is there, the internal energy may change. Therefore, the change in internal energy of the gas du can be due to temperature change, can be due to volume change. This is the change in internal energy due to temperature change. How? Right, dou u by dou t at constant volume into dt is the change in internal energy due to temperature change when the volume is kept constant into change in temperature, plus this is the change in internal energy due to change in volume at constant temperature, and this is the change in volume. So, this is the total change in internal energy due to volume change, this is the total change in internal energy due to temperature change, and this is the total change in internal energy due to both the changes, okay. But in this constant volume process, volume is constant, change in volume is 0. Therefore, dV is equal to 0. If you substitute here, this term becomes 0. 0 into this becomes 0. So, only you have this term. So, du is equal to dou u by dou t at constant volume into dt, okay. Dou u by dou t at constant volume into dt, equation 7. Now, I am comparing equation 3 and equation 7, okay. When you compare the left hand side of both the equations is same, equating the right hand sides, dou q at constant volume is equal to dou u by dou t at constant volume into dt, right. Now, bringing this to this side, dou q by dou t at constant volume, which we have defined already as CV, is equal to dou u by dou t at constant volume, okay. I brought dt to this side. So, dou q by dou t at constant volume, which we have already defined as CV, CV is equal to now dou q by dou t at constant volume is equal to dou u by dou t at constant volume. So, this is the formula for heat capacity of a gas from first law of thermodynamics, okay. As a result of the application of first law of thermodynamics for a constant volume process, you have another formula for CV, right, which is given by CV is equal to dou u by dou t at constant volume. CV is equal to dou q by dou t at constant volume is the formula for the definition, and CV is equal to dou u by dou t at constant volume is the formula which you got as a result of application of first law for isochoric process, right. Now, CV, right, just like heat capacity is an extensive property, okay, right. It depends on the mass of the system, and the units, the SI units are joule, energy is measured in joule, temperature in Kelvin, joule per Kelvin are the SI units of CV, right. Now, coming to molar heat capacity of the gas at constant volume, okay, molar heat capacity of the gas at constant volume, okay. CVM, molar heat capacity at constant volume, is nothing but the ratio of heat capacity of the gas to the number of moles. The ratio of heat capacity of the gas to the number of moles is called molar heat capacity, is equal to 1 by n into dou u by dou t. CV is how much? Dou u by dou t at constant volume, right. Okay, this is the formula for the molar heat capacity of a gas at constant volume, right. Okay. So, whenever the extensive property CV is divided by the number of moles, means mass, right. Okay, another extensive property, the ratio of two extensive properties will become an intensive property. So, therefore, all molar properties are intensive properties. So, molar heat capacity of a gas is an intensive property, whereas heat capacity of a gas at constant volume is an extensive property. So, CVM is an intensive property, and what are the units? Right, the units of CV are joule per Kelvin, and divided by moles, then it becomes joule per Kelvin per mole, are the SI units of the molar heat capacity at constant, right. Okay, CV is an extensive property and its units are joule per Kelvin, but CVM is an intensive property and its units are joule per Kelvin per mole, okay, joule per Kelvin per mole. Now, let us see the PV diagram of isochoric process. Here, in the isochoric process, volume is constant. Therefore, throughout the process, the volume, right, okay, which is shown on the x-axis, right, remains constant throughout the process. This is the initial volume, and throughout the process, the volume is same. Therefore, it is a straight line parallel to y-axis. since it is a straight line parallel to y-axis, right, its slope is always infinity. The slope of the PV diagram of isochoric process is always infinity, because the PV diagram of isochoric process is a straight line parallel to y-axis. Always slope is measured with respect to positive x-axis. Therefore, here the line, right, since it is parallel to y-axis, is making an angle of 90 with x-axis. Tan 90 is infinity, therefore the slope is always infinity, right? Okay. So this is about the isochoric process. Now I will start the applications, right, for isobaric process. Now I am discussing about the applications of first law of thermodynamics to isobaric process. Isobaric process means pressure is constant. In this process, pressure of the system is constant. P is equal to constant. Okay. Then what happens to the mechanical work done? dW is equal to minus PdV. As P is constant, you can take inside the derivative, minus d of PV. Because P is constant, you can write it outside the derivative or you can take inside. Its value will not change. So in place of minus PdV, the work done formula can be written as minus of d of PV. Substituting this in first law equation, du is equal to dq plus dw. In place of dw, I am writing minus of d of PV. I bring this to this side, it becomes du plus d of PV is equal to dq. So d of u plus PV is equal to dq, because du plus d of PV is like dx plus dy, dx plus dy, dx plus dy, which is equal to d of x plus y. Like this you can write, right? So therefore, du plus d of PV I have written as d of u plus PV. This quantity in brackets is defined as a new thermodynamic property called enthalpy H. U plus PV is now defined as a new thermodynamic property called enthalpy of the system, H. Okay. So in place of u plus PV here, I am writing H. Therefore, dH is equal to dq at constant pressure. dH, in place of this I have written H. So dH is equal to dq at constant pressure. This is the application of first law for isobaric process. Now you recollect what is the application of first law for isobaric process? It is du is equal to dq at constant volume. But here it is dH, right, is equal to dq at constant pressure. Okay, right? Now if the changes are significant, measurable, then the same dH can be written as delta H. Okay, and the same quantity dq, for which is representing small amount of heat interaction at constant pressure, now is written as amount of heat interaction, total amount of heat interaction at constant pressure. Okay. So this is the application of first law for isobaric process. Now earlier we have defined heat capacity, and also we have defined what is heat capacity of a gas at constant volume. I told you, right, heat capacity of a gas at constant volume is differing by a significant value when compared to heat capacity at constant pressure. So Cp is defined as dou Q by dou T at constant pressure. The amount of heat added to some amount of gas to rise its temperature by 1 degree at constant pressure is defined as heat capacity of a gas at constant pressure. Right? Now, if you take any gas, for any gas, the enthalpy of any gas depends both on temperature and pressure. Okay? If you remember, right, internal energy of any gas depends both on temperature and volume, whereas enthalpy of any gas depends both on temperature and pressure. So therefore, enthalpy of a gas will change either due to temperature changes or due to pressure changes. Therefore, writing the change in total change in enthalpy of the gas as the sum of change in enthalpy due to temperature change, change in enthalpy due to pressure change. Here, when you are calculating the enthalpy change due to temperature change, you are keeping pressure constant into the total change in temperature. Okay, plus this is the change in enthalpy due to pressure change when the temperature is kept constant into total change in pressure. Okay, so this is the change in enthalpy due to temperature change. This is change in enthalpy due to pressure change. Both they sum up to, right, the total change in enthalpy due to both the changes. So in this process, pressure is constant. So change in pressure is 0. So substituting here 0 into this value becomes 0. The second term becomes 0. Therefore, you are left with the first term only. dH is equal to dou H by dou T at constant pressure into dt. Now I am writing this as equation 13. Now comparing 10 and 13, you can see, right, the left hand side is same. Therefore, equating the right hand side. So dq at constant pressure, right, okay, is equal to this, right. Therefore, bringing this to this side, right, it is nothing but Cp dou Q by dou T at constant pressure. We have already defined as Cp. Cp is equal to dou Q by dou T at constant pressure is equal to dou H by dou T at constant pressure. So this is the definition of Cp. Cp is defined as dou Q by dou T at constant pressure, whereas from the first law, application of first law to isobaric process, Cp is defined as dou H by dou T at constant pressure. Cp is defined as dou H by dou T at constant pressure. Okay, right. Now let us calculate, right, the work done. Before already I told you heat capacity is a extensive property. The units are joule per Kelvin, right? Okay, right. Now, right, okay, if you go for molar heat capacity, right, okay, I forgot to write here, molar heat capacity, CPM of the gas at constant pressure is nothing but Cp by N, Cp by N moles, okay, 1 by N into Cp, how much you got? Equation 14, dou H by dou T at constant pressure, okay. Cp is an extensive property, but this molar heat capacity, right, is an intensive property, okay. The Cp units are joule per Kelvin, whereas the molar heat capacity units are joule per Kelvin per mole, okay, right. Now we are calculating the work done, right. In isochoric process, we have not calculated the work done because the work done is always 0, okay. In isochoric process, as volume of the system is constant, no expansion work, no compression work, therefore work done is always 0, okay. And right, what is the heat interaction? Heat interaction at constant volume in isochoric process is nothing but the internal energy change, delta U, okay, right. Now here we have to calculate work done because here in this process work done is not 0, therefore we are calculating the work done. First we are calculating the work done in reversible isobaric process, then we are calculating the work done in irreversible isobaric process. You can ask me why you are calculating separately, okay, right, because work is a path function, right. Why we are calculating separately, right, work is a path function, it depends on the path in which the process is taking place, okay, it depends on the path in which the process is taking place. As this process is taking place in a reversible path, the work done is different from this which is taking place in an irreversible path. So therefore, first we are calculating a work done in this reversible process. Here the reversible isobaric process is taking place from state 1 to state 2 in N moles of ideal gas, okay. The process is taking place, the process is reversible isobaric process, it is taking place from state 1 to state 2, and what is the system? N moles of ideal gas. The system is N moles of ideal gas, the process is reversible isobaric process from state 1 to state 2. But you know that for any reversible process, the work done is given by W is equal to minus integral 1 to 2 PdV, right. Whenever you calculate the work done in any reversible process, you have to use this formula, W is equal to minus integral 1 to 2 PdV, okay, right. Here the process is taking place from state 1 to state 2. For any reversible process, the work done is given by this formula. Now in this process, pressure is constant. In this process, pressure is constant. Therefore, taking pressure outside the integral, okay, integral 1 to 2 dV, right, which is equal to how much? Minus P into V2 minus V1, because volume is a thermodynamic property, right, and every thermodynamic property is a state function, right. Therefore, dV is integrable from state 1 to state 2 and its value is how much? V2 minus V1. So, integral 1 to 2 dV is how much? It is integrable, and after integrating it, you will get the value V2 minus V1. In state 1, the volume is V1, the state 2, the volume is V2. So, this is the formula for the work done in any reversible isobaric process, in any reversible isobaric process. But since this isobaric process is taking place in N moles of ideal gas, you can also rewrite this formula like this, okay, right, because this is nothing but what? First term is PV2, second term is PV1, okay. By using ideal gas equation, right, isobaric process, PV is equal to nRT, you can write PV2 as nRT2, you can write PV1 as nRT1, therefore taking nR common minus nR common, it is T2 minus T1. This is another formula for work done in a reversible isobaric process. But you can use this formula given by equation 16 if the system is ideal gas, okay, right. But you can use equation 15 to calculate the work done in a reversible isobaric process, whatever may be the system. The system may be anything, okay, you can use this formula. But if the system is ideal gas, then this formula can be recast in this manner. It can be rewritten in this manner, minus nR into T2 minus T1. Okay, sometimes in entrance, he will ask a question by giving this initial volume, final volume and pressure, then you can use this formula. Okay, if he gives temperatures, initial temperature and final temperature, right, then right, if it is a ideal gas, n moles of ideal gas, then you can use this formula. So depending on the question asked in the entrance exam, we have to use either this one or this one, okay, right. Then coming to irreversible isobaric process, right. Now an irreversible isobaric process is taking place from state 1 to state 2, again in n moles of ideal gas. Again the process is taking place from state 1 to state 2, but now it is taking place in an irreversible path. It is an irreversible isobaric process, and now the system is ideal gas, n moles of ideal gas, right. Okay, then for any irreversible process, the work done is given by minus P opposing into V2 minus V1. This is the external pressure or opposing pressure, right. Okay, opposing the process, and this is the initial volume V1 in state 1, this is the final volume V2 in state 2, okay, right. This is the formula which you can use for any irreversible process to calculate the work done in any irreversible process. But here, right, this is an irreversible isobaric process taking place in n moles of ideal gas. Therefore, using gas equation, V2 can be written as nRT2 by P, and V1 can be written as nRT1 by P using gas equation, right. Okay, so nR by P you can take outside, nR P opposing by P into what is left now, T2. Here what is left, T1, T2 minus T1. Like this also you can write the work done in a irreversible process, but the equation 18 is applicable, okay, only when the irreversible isobaric process is taking place in ideal gas, okay, in ideal gas. Otherwise, you have to use only this formula given by equation 17, right. Now coming to the PV diagram. The PV diagram of isochoric process we have seen already, which is a straight line parallel to y-axis. Now the PV diagram of isobaric process is also a straight line, but now it is parallel to x-axis. It is parallel to x-axis, right. Okay, here P is constant, pressure is shown on the y-axis. This is the initial pressure, and throughout the process the pressure is same. Therefore, it is a straight line parallel to x-axis. Since it is a straight line parallel to x-axis, the slope of this PV diagram is always 0. Okay, if you remember what is the slope of PV diagram of isochoric process, it is always infinity because it is parallel to y-axis. Now its slope is 0 because it is always parallel to x-axis, right. Okay, so this is about the application of first law, right, for isobaric process, right. Okay, so right, okay, here what are the questions which you can expect? He can ask you question on the applications, right. In the entrance exam, he can ask you on the application of first law for isobaric process. What is the application? Delta H is equal to QP, okay, right. There delta U is equal to QV, okay, right. Then he can ask you what is the CP formula, right, according to the application of first law for isobaric process. CP is how much? Dou H by dou T at constant pressure, and he can ask whether it is extensive property or intensive property. It is extensive property, okay, right. Whereas what is CV formula, right, for the application of first law in isochoric process? CV is equal to dou U by dou T at constant volume, okay. Then he can ask you what is the work done in isochoric process? The work done is always 0, okay. Here what is the work done? Reversible isobaric process separately we have calculated, irreversible process, isobaric process separately we have calculated. If the system is ideal gas, again we have written another formula. In place of 15 we have written 16. If it is ideal gas, in place of 17 you can use 18, okay. And then he can ask you about the PV diagram, right. What is the PV diagram? The PV diagram of isobaric process is a straight line. So like this, any question he can ask, right, on the first law, right, applications for isobaric process, right, or isochoric process, right. Now I am continuing the applications of first law. Now we are studying the most important application, that is for isothermal process. While studying isothermal process, we are considering n moles of ideal gas as the system during this process, right. For ideal gas, there is an important result from Joule experiment. The result from Joule experiment states that internal energy of ideal gas depends only on temperature. It does not, for any gas, internal energy depends both on temperature and volume, but for ideal gas, internal energy does not depend on volume changes, it depends only on temperature changes. But in this process, temperature is constant, okay, and therefore, as temperature is constant, internal energy remains constant. Therefore, U is constant, that implies du is equal to 0, change in internal energy is 0. So in this process, isothermal process, when you are considering ideal gas as the system, the internal energy always remains constant and the change in internal energy is 0. This is a very important objective question repeatedly asked in the entrance exams, right? Okay. Now coming to the first law, du is equal to dq plus dw, but du is 0 in this process, therefore substituting here, right, you will get 0 is equal to dq plus dw and dq is equal to minus of dw. Okay, this is the application of first law for isothermal process. For measurable changes, okay, for significant changes, you can write q is equal to minus of w. Okay, you can write q is equal to minus of w. Okay, right. So, right, okay, this is the application of first law for isothermal process. Now, we are studying two important cases which are very, very important in all the entrance examinations, right. What are the two cases? First one, if the work done is a positive work, here according to the IUPAC sign convention, what is positive work? Work done on the system. Okay, when the system gains energy in the form of work done on the system or compression work is taken as positive work. Okay, so here compression, which compression? Here isothermal process, therefore isothermal compression. So positive work here means it is reversible isothermal compression. Then as W is positive, according to equation 22, Q is equal to minus W. Now W is positive, therefore Q is equal to minus of positive. Minus into plus is how much? Minus. Q is equal to minus. Okay, right? Heat interaction is negative. According to IUPAC sign convention, if heat is given out by the system, we are taking minus sign. If heat is received by the system, then we are taking plus sign. Here Q is minus, means in this process, Q is minus means what? Heat is given out by the system. Why? As a result of reversible isothermal compression, as a result of isothermal compression, always the system gives out heat, rejects heat to the surroundings. Right? Okay, right? So first question you can ask in the entrance exam is, what is the, right, okay, result of positive work done during a reversible isothermal process? The result is, right, okay, right, temperature increases, temperature decreases, right, heat is, right, received by the system or heat is given out. Like that he can give 4 options. Okay, when a positive work is done during isothermal process, right, option A, right, temperature of the system increases. Option B, temperature of the system decreases. Option C, heat is received by the system. Option D, heat is given out by the system. Right here, right, what is the result? Heat is given out by the system. Okay, right. So why? Another question you can ask is, as a result of reversible isothermal compression, why heat is given out by the system? Okay, right. Now I will explain this very clearly. Right, here in this process, right, temperature should be constant, but what is happening? Work is done on the system. System is receiving, because work is done on the system. System is compressed, right? System is receiving energy in the form of work. As system receives energy in the form of work, its internal energy increases, right? As internal energy depends on temperature, right? Okay, therefore temperature increases, but temperature should be kept constant. So to keep temperature constant, the system starts giving out heat. It starts rejecting heat. Okay. So why a system is giving out heat in an isothermal process? In an isothermal process, the system is giving out heat to maintain the temperature constant. Because it is an isothermal process, temperature should be constant. To keep the temperature constant, the system is giving out heat as a result of reversible isothermal compression. Now let us see the second case. Right? If work done is negative work. Negative work means what? According to IUPAC sign convention, okay, right? When energy is lost, right, energy is lost by the system, it is taken as minus. Okay, right? When work is done by the system, right, by expanding, then what happens? It's energy loss. Therefore, right, that is taken as negative work. So therefore, expansion work or work done by the system is taken as negative according to IUPAC sign convention. Therefore, here negative work means what? Reversible isothermal expansion. Okay, then what happens? According to first law application, Q is equal to minus W. So Q is equal to minus of, what is the work done now? Minus negative. Minus into minus plus. So therefore Q is plus. Q is plus means according to IUPAC sign convention, right, Q is taken as positive when heat is added to the system, when heat is received by the system, when energy is gained by the system in the form of heat. Therefore Q is positive. Right? Now when Q is positive as a result of this process. So when reversible isothermal expansion takes place, when a negative work is done during isothermal process, the system absorbs heat, the system receives heat. Okay, right? Now why it receives heat? Why the system receives heat as a result of reversible isothermal expansion? Okay, again I will explain this. Here in this process temperature should be constant because it is isothermal process. But now what is happening? System is expanding and is doing work on the surrounding, therefore it is losing energy in the form of work, therefore its internal energy decreases, and as a result its temperature decreases. But to keep the temperature constant, the system starts receiving heat, right? Okay, to keep the temperature constant, the system starts receiving heat, absorbing heat. Okay, so therefore, why the system is receiving heat, absorbing heat in this process? To keep the temperature constant. To maintain the temperature of the system constant, the system is absorbing heat as a result of reversible isothermal expansion, or during negative work done during isothermal process, reversible isothermal process, right? What happens? Always heat is received by the system. Why heat is received by the system? To maintain temperature constant. Okay, right? Now we are calculating the work done, right? Okay, then I told you work done is a path function, right? Therefore, we have to calculate the work done separately for reversible isothermal process and also for irreversible isothermal process. For any reversible process, the work done is given by the formula minus integral 1 to 2 p dV. Okay. Now, the reversible isothermal process is taking place from state 1 to state 2 in n moles of ideal gas. Therefore, in place of P, I am writing nRT by V using ideal gas equation. N is constant, R is constant, T is constant, taking outside the integral. Integral 1 by V dV is a standard integral. Integral 1 by x dx is how much? Log x plus integration constant. Okay. So, similarly, right, using integral 1 by V dV, same formula you will get log V. Between the limits 1 to 2, you will get V2 by log V2 by V1. Okay, right. So, minus nRT into log V2 by V1. Right. Okay. So, right. Okay. Integral 1 by V dV, right, log V plus integration constant. Okay, right. So, between limits, if you do integral V1 to V2, 1 by V dV, then it becomes log V between limits V1 to V2, integration constant becomes 0, log, substitute upper limit, log V2, minus, substitute the lower limit in place of V, log V1, log A minus log B is log A by B, log V2 by V1. Like this, you will get this log V2 by V1. Now, if you here, what is the base? Base is E, log with base E. Now, if you convert into base 10, you will get 2.303. So, minus 2.303 into nRT log V2 by V1 base 10. Right? From Boyle's law, right? Okay, when temperature is constant, right? You have P1 V1 is equal to P2 V2. So, in place of V2 by V1, you can write P1 by P2. Therefore, the same formula can be rewritten as log minus 2.303 nRT log P1 by P2 base 10. Now, coming to irreversible isothermal process. For any irreversible isothermal process, you can use this formula. Even for this process also, you can use this formula. But since this process is taking place in n moles of ideal gas, by using gas equation, V2 can be written as nRT by P2 and V1 can be written as nRT by P1. Okay. Taking nRT outside, you will get 1 by P2 minus V1. So, this formula can also be used for irreversible isothermal process provided the system is ideal gas. Okay. Now, coming to heat interaction. How to calculate heat interaction? Right, according to this formula, Q is equal to minus W. So, therefore, for a reversible isothermal process, again heat interaction, Q is a path function, just like work. Okay, it is a path function. Therefore, you have to calculate separately for reversible isothermal process and irreversible isothermal process. So, Q reversible is equal to minus W reversible. W reversible we have already calculated, minus 2.303 nRT log V2. Substituting here, you will get minus into minus plus nRT log V2 by V1. Now, for irreversible isothermal process, Q irreversible is equal to minus W irreversible. W irreversible already we have calculated here. Okay, right? W irreversible we have already calculated here. Substituting this formula here, minus into minus becomes plus P opposing nRT into 1 by P2 minus P1. Right? Okay. And how to calculate? Right? Okay. We have calculated work done. We also calculated heat interaction. We have to calculate change in internal energy. We have to calculate change in enthalpy. Okay. Delta U and delta H calculation. But for ideal gas, according to Joule experiment, internal energy depends only on temperature. Enthalpy also depends only on temperature. As temperature is constant, delta U is 0, delta H is 0. In which process? Okay. Just like work done and heat interaction, shall we calculate separately for reversible process and irreversible? No need, because U and H are thermodynamic properties. They are only state functions, they are not path functions. Therefore, they will have the same value for reversible isothermal process and irreversible isothermal process. This is a very, very important objective question, repeatedly asked in entrance examinations. For example, you take free expansion of a gas, free expansion of a gas. Free expansion of a gas is a irreversible isothermal process, is a irreversible adiabatic process. Therefore, right, okay, In that case, right, okay, delta U is 0, delta H 0. Okay, free expansion of ideal gas, right, okay, right, or free expansion of any gas, right, okay, delta U 0 and delta H is 0, okay, right. So, now because it is an irreversible isothermal process and also irreversible adiabatic process, right, okay. So, delta U 0 and delta H is 0, right, okay. So, for any process, right, okay, for any process, it may be irreversible isothermal process or it may be reversible isothermal process, delta U is 0 always, delta H is 0 always, okay. So, this is about isothermal process. Now, coming to the PV diagram, the PV diagram of isothermal process is a curve, it is not a straight line. In case of isochoric process, it is a straight line parallel to y-axis, right. In case of isobaric process, it is a straight line parallel to x-axis, but in case of this, it is a curve, okay, it is a curve. It is not a straight line, okay, right. So, this is about the isothermal process.